Welcome back to the deep dive. Today, we are really digging into Black Forest Labs' newest creation, the FLUX.2 image generation model.
Yeah,
And this isn't just, a simple update. This is a complete architectural overhaul. And it seems like it's designed to fix some of the biggest headaches in visual AI today.
that's the perfect place to start.
Yeah.
DFL has been really clear that this is a brand new architecture, trained completely from scratch.
So not a drop-in replacement for FLUX.1.
Not at all. They're positioning it as a new kind of tool for actual creative workflows.
Yeah.
Where things like precision, speed, and cost really, really matter.
Okay, so our mission for this deep dive is to basically dissect this thing. We want to understand the architecture, look at the really surprising new ways you can control it, and maybe most importantly, figure out how on earth they've made this incredibly demanding model usable for people with normal hardware.
Exactly. The promise is realism and precision, and we're going to see how they've pulled it off.
And this all fits into their bigger picture, right? Their open core idea.
It does. They're trying to do both things at once. They're pushing the frontier with something like FLUX.2, but they're also committed to open research by releasing inspectable open-weight models.
Like the big 32 billion parameter one.
The FLUX.2 dev, yeah. So they want the research to be out there, even if the absolute top-tier version needs, serious infrastructure to run.
Okay, let's unpack that. I mean, we've had pretty good image models for a while. If they went to the trouble of rebuilding this thing from the ground up, what were the big problems they were trying to solve?
I think it really comes down to unifying a bunch of different functions and getting way, way better consistency.
Okay.
So this one single FLUX.2 architecture can now handle image data generation, your standard text-to-image, and really complex image editing from text, and this is the crazy part, from multiple visual references at once.
So you don't need 3 different models or some complicated workflow anymore.
Right. You used to have to chain things together. Now it's all one cohesive system.
That's a lot to ask from one model, though. Usually when you try to make a tool do everything, it doesn't do any one thing perfectly. You get trade-offs.
You do, but it seems like they avoided that by focusing the whole architecture on what they call deep contextual integration.
Yeah.
We can get into the nuts and bolts of that in a bit.
Okay.
But the result for you, the user, is 4 huge improvements that they get rid of old frustrations.
All right, lay them out for us. What are they?
First one, reliable text rendering. This is massive.
Oh, finally.
Yeah. I mean, models could sort of do one word, but they would just fall apart on anything complex. Infographics, memes, UI mockups. FLUX.2 can now generate legible, fine text, even inside a really busy image.
That right there changes the game for anyone doing marketing or design work.
Totally. Second one, multi-reference support.
Yeah.
This is the consistency breakthrough. You can feed it up to 10 different images at the same time to guide what it creates.
10 images.
10. So if you're trying to keep a character looking exactly the same, or a product's texture, or a very specific artistic style across a dozen shots, using 10 references pretty much guarantees it.
It's like giving it a whole mood board instead of just one photo.
It's precision, not just inspiration. Then third, there's the resolution. It can generate and edit images up to 4 megapixels. That's a big deal for professional work.
Right, 4MP is a usable threshold.
And finally, enhanced world knowledge. The model just has a much better grasp on reality. Things like lighting, physics, how objects should be arranged in a room. It leads to way more believable scenes.
Okay, that versatility is clearly the big story here. Before we get into the tech that makes it possible, can you give us a quick map of the different versions? Who gets to use what?
Sure. The family is kind of tiered. At the top, you have FLUX.2 Pro. That's the best quality, highest speed, lowest cost. You get that through an API or their launch partners.
For the big production houses.
Exactly. Then for developers, there's FLUX.2 FLEX. That one lets you tweak the parameters yourself, like the number of steps or the guidance scale.
So you can choose between speed and quality.
Right. Do you want a quick 6-step generation or a super detailed 50-step one? You decide.
And what about the rest of us who just want to run this at home?
That's where FLUX.2 dev comes in. That's the big 32 billion parameter open weight model. It's released under a non-commercial license for anyone to experiment with.
Okay.
And they've also announced a FLUX.2 client is coming soon.
Right.
That'll be a smaller, distilled down version with a fully open source Apache 2.0 license.
Now we get to lift the hood. The model's performance is obviously impressive, but what did they actually change in the architecture to get that kind of control?
So the shift is really interesting because they actually simplified one part of it while making another part way more complex.
Okay.
Let's start with how it understands text. FLUX.1 actually used 2 different text encoders. FLUX.2 simplifies that down to a single one. Mistral Small 3.1.
Fewer cooks in the kitchen. That makes sense.
Exactly. And they made that one encoder work a lot smarter.
Yeah.
It takes a long text input, sure, but the key is that it uses stacked outputs from the intermediate layers of the transformer.
What does that mean, intermediate layers?
So instead of just taking the final understanding of the whole prompt, it pulls in nuanced information from earlier stages of processing. It gives the model a much richer, more granular understanding of your instructions.
That's the text side. What about the actual image creation part? Still diffusion transformers.
It is, yeah. The core is a multimodal diffusion transformer, or MMDIT.
Mm-hmm.
But how it's structured is the whole story. It has two different kinds of processing blocks.
Remind us what those are.
You've got double stream blocks, where the image data and the text data are processed mostly separately. They kind of check in with each other, but they're in their own lanes.
Okay.
Then you have single stream blocks,
Yeah.
where the image and text data are smashed together and processed as one single thing. It's a much deeper fusion.
And I'm guessing FLUX.2 shifted the balance there.
Dramatically. FLUX.1 was pretty balanced between the two. In FLUX.2, there are 8 double stream blocks and 48 single stream blocks.
Wow, that is a huge shift.
It is. If you looked at that 32 billion parameter model, something like 73% of its entire weight is now in those single stream blocks,
73%.
up from about 38% in the last generation. It's a massive bet on deep, constant, joint image text processing. That's why it's so good at following complex prompts.
That really is a statement of intent. Now, what about this? This other little detail I saw, the elimination of bias parameters. That sounds really technical. Why would they do that?
Yeah, that's a real deep cut detail. So bias parameters are standard in basically all neural networks. They help shift the output of a neuron to help it learn better.
Okay.
Getting rid of them is a very clean, deliberate architectural choice. While BFL hasn't given the exact reason, removing bias can make the model more numerically stable, especially when you're training with low precision, and it trims a few parameters.
So it's like sacrificing a little bit of flexibility during training for a more robust, stable, and efficient model in the end. It's that production-ready thinking again.
Precisely. And just to round out the picture, it also uses a new autoencoder, and it's built on what's called a latent flow matching architecture.
Which in simple terms means?
It's a newer technique that lets the model generate the final clean image more directly, which often means faster and more stable results than older methods.
Okay, so we have the foundation. Let's bring it back to the user. The absolute peak of control isn't just understanding a sentence, it's commanding specific elements. How does it do that?
This is where it gets really cool. They're pushing this idea of structured JSON prompting.
So you're not just running a sentence anymore.
No, you're giving it a structured file, like a dictionary, that breaks down every part of the image. The scene, the subjects, the style, the camera settings, the lighting.
You're basically programming the image.
It's pretty close.
Yeah.
And it gives you this surgical control. You can have a prompt with 30 different attributes,
Mm-hmm.
and then you can change just one of them, and the other 29 will stay locked in place.
Let's walk through that example from the sources. So we're doing a product shot.
Right.
We start with a JSON prompt. It describes a silver Sony Walkman on a carpet. And we're super specific with the camera. High angle, 85 millimeter lens, f5.6 aperture.
So you've locked in the style, the lighting, everything. Now the art director says, I don't like the carpet color. In a normal model, you'd type, change the carpet to teal and hope for the best.
And the whole image would probably change.
Exactly. Here, you just go into the JSON file and edit the color attribute to a specific hex code, hashtag 367588.
And then crucially, we need to add another object without messing up the whole shot.
Yep. So you just update the JSON, you add a second subject, wired headphones coiled up next to the Walkman, and the model does it. It changes the carpet to that exact shade of teal blue, adds the headphones with perfect lighting and shadows, and keeps everything else exactly the same. The f5.6 aperture, the 85 millimeter lens, all of it.
That's the leap. That is what moves this from a fun toy to a serious commercial tool.
It's the difference between suggestion and instruction.
Okay, we have to talk about the elephant in the room. The hardware. This kind of power costs a lot of computational energy. The sources say the raw model is a beast.
It's a monster. It's a data center model, plain and simple. If you just try to run the 32 billion parameter version without any tricks, you need more than 80 gigabytes of VRAM.
80.
Yeah, even on a top-of-the-line NVIDIA H100 GPU, if you try to offload some of it to the CPU, you're still looking at around 62 gigs of VRAM. That's just not something people have at their desk.
So what does this mean for the person listening who has, say, an RTX 4090 with 24 gigs or even less?
Yeah.
How do you bridge that gap between 80 gigs and, reality?
And this is where the open source community, working with platforms like Diffusers, becomes absolutely critical. They've built a whole suite of memory-saving tricks just for FLUX.2.
Let's break those down. What's the first step for someone with a good consumer card?
The first and most common technique is 4-bit quantization. You use a library like bit-sandbytes. Essentially, you're compressing the model's weights. Instead of storing each number with 32 bits of information, you only use 4.
And what does that do to the VRAM usage?
It's a huge drop. Suddenly, if you have a 24-gig GPU, like a 4090, you can run the whole model locally. It takes up about 20 gigs of free VRAM.
So it's tight, but it's possible.
It's possible. But what if you need a bit more headroom?
Okay.
The next trick is local plus remote inference. Remember we said the model has that one single text encoder?
Great, the Mistral one.
So that part, while it's not huge, it still takes up VRAM. With this technique, you can run just that text encoder on a remote server, like a cloud endpoint.
Ah, so you offload the thinking part, and your local GPU only has to do the heavy lifting for the image creation.
Exactly. You just run the DIT and the VAE locally, and doing that brings the VRAM requirement down again to about 18 gigs.
That's a clever hybrid approach. But now for the magic trick. How do they get it to run on a standard 8-gigabyte card?
This is the most complex one, group offloading. This is the technique that makes it accessible to almost anyone. It lets you run it on a GPU with as little as 8 gigs of free VRAM.
I'm sorry, you went from 80 gigs in a data center to 8 gigs on my gaming PC. That sounds impossible. What's the catch?
The catch is your system RAM and speed. The model is too big to fit in 8 gigs of VRAM, so it's constantly swapping pieces of itself back and forth between your fast GPU VRAM and your slower system RAM.
The normal RAM sticks connected to the motherboard.
Exactly. And to handle all that swapping, you need at least 32 gigabytes of system RAM.
And I assume it's slower.
It is noticeably slower, yes. You can even do it with just 10 gigs of system RAM, but it gets even slower then. The point isn't speed, though. The point is that it runs. You can experiment with a state-of-the-art model on very modest hardware.
That is an incredible win for accessibility. It really is.
It really shows the power of the open source community to optimize these giant models. And a quick side note, if you're lucky enough to have a new Hopper series GPU, you can speed things up with an optimization called Flash Attention 3.
Okay, last big use case, fine-tuning. If just running the model is a challenge, training it with your own images must be even harder.
It's an order of magnitude harder, yeah. To do it, you basically have to throw every single optimization trick at it at the same time.
So you're using the remote text encoder, the CPU offloading.
All of it. And you add another trick called latent caching.
What's that?
So to train the model, you first have to use the VAE to encode all your images into the latent space. Latent caching just means you do that once up front. You pre-process all your images, save those tiny latent files, and then you can actually delete the VAE from memory during the training run itself.
Freeing up another big chunk of VRAM.
A huge chunk. And of course, you have to use low precision training. There's no other way.
What you mean?
You're either using FP8 training, which needs very new specific hardware, or you're using the more common NF4Q LoRA method, which uses those 4-bit quantization techniques we talked about to drastically cut down the memory needed for training.
And as these tools become more common, we have to talk about responsible use.
Absolutely. Black Forest Labs says they're committed to it. They've built in the ability to embed invisible watermarks into the images.
Okay.
And they strongly recommend everyone uses the C2PA standard. That's the Coalition for Content Provenance and Authenticity. It adds metadata to the file that permanently marks it as AI generated and shows its origin.
We've covered a ton of ground here. For me, the big aha moments were definitely the architectural stuff. That huge shift to single stream blocks and the weird decision to just remove bias parameters.
Yeah.
That and the JSON prompting, which is just a whole new level of control.
I think if you zoom out, FLUX.2 really feels like a big step toward a true multimodal model. It's not just making pictures anymore. It's unifying perception, reasoning through text, memory with the multi-reference system, and highly controllable generation. All in one open architecture.
Exactly. So that leaves us with a final thought for you to chew on. Now that we have models that can reliably follow surgical instructions, we're talking specific hex codes, camera lenses, object placement, all in one, go what new kinds of hyper-specialized artistic or even commercial tools become possible when AI generation finally moves from being a suggestion to being an instruction. We'll leave you with that.